Hey, welcome. Thanks for coming to this talk about the GraalVM and what GraalVM means for the Eclipse IDE. My name is Martin. I work for Pivotal, for the Spring Engineering Group, working on Spring tools. So you might wonder why am I talking about GraalVM, but you will find out in the end. And before we start, quick question: who is already familiar with GraalVM and knows most of the stuff that GraalVM does? Only a few of you? Okay, yeah, a little bit here and there, heard of stuff. That's good. I will give a quick intro, and then we will get started. Okay, so what is this GraalVM thing at all? First, it's that's kind of the marketing slide from Oracle. It's an open source project from Oracle. It's a high-performance polyglot virtual machine. So the goal is to run basically any language on top of a unified virtual machine that compiles stuff, like all the languages, into super extremely well-optimized, high-performance code, and can run all these languages like Java and JavaScript and Ruby and even C++ and things like that. The interesting piece of that is that the idea is to run that in a kind of a unified virtual machine that can execute all those languages at the same time. So there are no boundaries between the languages. So the idea is there is no, if you run Java and JavaScript in the same virtual machine, they're not running side by side, but they're really running together, accessing the same objects and things like that. So you don't get any kind of boundaries between them. Makes a lot of optimizations possible, a lot of improvements possible at the virtual machine level. So the idea in the middle, there's GraalVM. So basically, you throw all the languages at GraalVM, and GraalVM compiles all the stuff into high-performance code. And below that, you can. The idea is to use this GraalVM in different settings. So if you want to use that in regular open JDK setting, like you're running a Java virtual machine, but you would like to use this technology, you can do that. Like kind of you can embed Graal into the general OpenJDK, but you can also kind of replace the general Node execution environment, the V8 engine of Node, with GraalVM and run GraalVM as an embedded compiler for JavaScript in this Node environment, or inside an Oracle database, or, and that's maybe something you have heard of before, as kind of a native executable, a standalone native executable application. We'll come back to that a little bit later. At the center of all that, for GraalVM, that's what GraalVM kind of, what the name really comes from, is a highly optimizing compiler. So kind of that's, this compiler can compile, for example, Java bytecode into super highly optimized assembly code and machine code. Okay, that's maybe not super new, because if you're running OpenJDK or the HotSpot Java virtual machine, there are already compilers doing that, right? The big difference is if you grab the HotSpot Java virtual machine today, and you're looking at the compilers that are built into that, that are really kind of at the heart of the execution and at the speed of the JVM, they are written in C and C++, and they are, I think, there are only a few people left on the planet that understand how that all works. It's more or less not maintainable anymore and not improvable anymore. For most of the folks working on the JVM, it's really hard to add additional optimizations into that compiler technology. So there was a kind of a relatively old research project at Oracle where they tried to re-implement the whole Java virtual machine in Java, kind of a nice exercise, like implement a Java virtual machine in Java. So therefore, they built also a highly optimizing compiler in Java. And that's what's at the heart of the GraalVM is today. It's kind of a highly optimizing compiler that takes Java bytecode in this case, and maybe something else, and produces highly optimized machine code. And that whole thing is written in Java and relatively new compared to the old HotSpot stuff. So it can be easily maintained, improved, and there is a whole group working on that, putting tons of optimizations into that compiler that are maybe not even available in HotSpot or not even thinkable in HotSpot. This compiler provides additional API to the outside. We will see a little bit how that interacts with the outside world. But whenever people talk about GraalVM, it's not just ahead of time compilation or whatever. It's really, most of the stuff deals with these highly optimizing compiler that can spit out really fast machine code. It does a lot of optimizations under the hood. You can use that compiler as a simple replacement in the JDK. So if you download JDK 11, for example, you will see that you can just drop in the Graal compiler if you want that just as a compiler piece. The interesting question is, I've talked about this, oh yeah, you can use that as inside of an open JDK to compile Java bytecode into something else, into machine code. There is the idea of, okay, this compiler should also compile other languages, should be able to compile other languages, and therefore they implemented some kind of framework on top of the GraalVM. And this framework can talk to the API of the compiler, and this framework allows you to implement a compiler for your own language. So you don't need to build that from scratch, your own compiler for your own language. You can use this language implementation framework, or the truffle framework, what that was called, to basically build an AST-based interpreter for your language based on this framework. And GraalVM, the compiler, takes that and uses some super sophisticated technologies to turn that into super highly optimized machine code, which is really interesting because it's not kind of, doesn't seem to be obvious that you can do that, but there are research papers out there using partial evaluation of AST-based interpreters and things like that. If you want to know more, I can give you tons of references about that. It's really sophisticated stuff, but it's really interesting because you can implement your own language in a relatively easy way on top of this compiler. You don't have to figure out all the optimizations yourself. For example, what they did is they implemented JavaScript based on the truffle framework. So they wrote an interpreter for JavaScript based on ASTs. And in the end, the compiled machine code from the Graal compiler is comparable to the V8 engine that's inside of Chrome. Just to give you a hint of what I mean with talking about highly optimizing compiler and the highly optimized machine code that comes out of that. Even for something that's kind of something like a little bit strange language like JavaScript, if you implement it this way, the resulting engine using this compiler is really, really fast. So this is what the overview would look like. You get the HotSpot JVM and you kind of insert the Graal compiler into that. Kind of you more or less rip out the old C2 compiler in OpenJDK, and you put in the optimizing Graal compiler, and therefore it can deal with all these JVM languages as usual, applying all these optimizations. Good stuff, right? The question is that comparable with the C2 compiler in HotSpot? It is. It's actually up to kind of it differs a little bit here and there. Sometimes it's a little bit slower, sometimes it's a little bit faster, has some certain kind of, has a little bit of focus on these, let's say, Lambda and Stream APIs, where you have a lot of nested Lambda Stream structures that are super highly optimized with the Graal compiler, a lot better than HotSpot. Other things that running slightly better on the HotSpot C2 compiler at the moment, performance-wise. But the goal, of course, from the Graal team is, if we're not faster than HotSpot, then it's a bug for us. We need to fix that and improve the compiler. On the other side, there's this truffle framework that interacts with the Graal compiler in a specific way, and the languages are implemented on top of this truffle framework, just as in kind of a brief overview. So how can I use that? How can I just try it out myself? There are basically two ways to do that. You can go to the GraalVM homepage and just download the GraalVM SDK. And then you get more or less something like a replacement for your OpenJDK installation. You can use it as a drop-in replacement. So that's good. Easy to use. And if you do that, you will find out that there are a tiny little more executables in the bin directory, doing more stuff, and you can install additional packages, for example, to run R code, to run Ruby code, to run additional languages on top of this compiler. You just need to use a little installation tool that comes with this download. That's one way to use it. And I will do that quickly. So what I have here, a few examples, and if I say which Java, see that's coming from my Graal installation that I have. As you can see here, it's on JDK 8 level, so there's no GraalVM SDK implementation yet for JDK 9, 10, 11, 12, 13, 14, whatever. They're working on it, and it seems to be, they said it might come out this year, but it's not there yet. So just as kind of as a heads up. So let me quickly compile hello world Java, nothing really super exciting. We can take a look at that quickly. Hello world, right? What else? Let's do a hello world. Hello world. We can just see how long does it take to start that up. Round about that, pretty fast. JVM comes up, regular HotSpot, more or less regular HotSpot JVM with Graal compiler included, so it can compile stuff on the fly, and that's kind of the output. That's okay. It's pretty easy, simple to use, regular Java stuff, right? Nothing really sophisticated. And in the other case, I have a node application. Simple node application serving the hello world in the web. So when I take a look at my node executable, it's also coming from the GraalVM. So I'm not using the regular node installation. I'm using the node installation from Graal that comes with GraalVM. And that's not the regular node. It's GraalVM compiler embedded into this. So I can also do that. So runs the application on GraalVM, which is regular JavaScript stuff. So this JavaScript gets compiled with GraalVM into native machine code and it's being executed inside of the node environment. So that's also a nice thing. And what's even possible, which is a little bit strange and maybe counterintuitive, they also went ahead and say, okay, we would like to execute and compile C or C++. So what should we do about that? So let's see what do I have. Hello C. Nothing really super. That's up to my knowledge of C++, if I remember that correctly. I forgot the rest for a good reason. So let's compile that with Clang into bitcode. So let's emit LLVM bitcode for that. So it uses the LLVM tooling chain to compile that into bitcode. That's the BC one. And now I can use kind of an executable startup that uses the GraalVM, where GraalVM compiles the bitcode from LLVM into executable machine code in a highly optimized way, in the same way. So I can start that with the, let me prove that's really coming from the GraalVM thing. Yeah. Hello. Hello from GraalVM. So running 3 different languages on GraalVM, pretty nice. And the cool thing is that you can also, I don't have an example for that, but you can also go ahead and combine those languages into the same thing, right? You can run you can write your Java app, you can execute JavaScript inside that, accessing the same objects, the same space. That's pretty nice. Okay, so quick demo. That's using GraalVM to execute and compile all those different languages. There is, if you go to the GraalVM homepage, just a side note, there are 2 different editions. One is the Community Edition, so don't be surprised. That's free to use, free to download, open source. And there's the Enterprise Edition. That's payware from Oracle, so you have to pay for that. You have to buy a license and things like that. And the Enterprise Edition contains more performance improvements, so the compiler can do more stuff. Has more security improvements, security features inside if you want to run stuff in isolation and things like that. So a lot more features. Oops. Okay. So what does it mean for the Eclipse IDE? First, you can just go ahead and run Eclipse IDE on top of the Graal compiler. And you can do that by downloading JDK 11. Maybe you already have that installed. Maybe you're already running Eclipse on JDK 11. And if you're running Eclipse on JDK 11, you can just put these flags into the startup options, into the ini file. That enables the Graal compiler as a replacement of the C2 compiler in the regular OpenJDK. So the Graal compiler already comes as part of the OpenJDK 11 distribution, but as kind of a silently hidden small feature that you can enable with these flags that uses the Graal compiler as a replacement for the C2 compiler. Attention, it's sort of an older version, of course, because it's the version that was around when JDK 11 got released, or with the latest update of JDK 11. So it's not the latest and greatest GraalVM compiler, but you can use it if you want to. You will basically, if you run your IDE, you will not really notice anything. There's no big difference. It more or less runs at the same speed. You will not say, oh my God, it starts up twice as fast, or oh my God, build workspace I don't see the build workspace progress bar anymore, or things like that. It's more or less kind of the same, right? It's up to the same, more or less to the same performance level. That's one way. The other way is you can download the GraalVM SDK distribution, which is also basically an OpenJDK with the GraalVM compiler enabled by default as a C2 compiler inside, and you will be able to add these additional languages to the installation. But for running Eclipse, it's also it's basically the same, but you will get a newer and maybe the latest and greatest version of the GraalVM compiler to run that. You can use that as a regular OpenJDK replacement if you want to. You can do that. But you will probably also not really notice any meaningful difference in execution speed. Nothing that you will immediately see or feel, which is explainable because most of the Eclipse IDE doesn't really use a lot of these constructs that the GraalVM compiler really focuses on and can do a lot of stuff. And maybe it takes more time for GraalVM compiler to improve and add additional optimizations for everything and for the different patterns that are, for example, used inside of the Eclipse platform, for example. But that's just me guessing around. In the end, you will, at the moment, not really see a big difference. The question is, some crazy thought. If GraalVM is able to execute different languages, would it make it easier for you to implement plugins for Eclipse in different languages? So hey, great, now I'm really able to implement my Eclipse plugin as in JavaScript. You can do that, and this JavaScript would be executed at really high speed, which would be good, but you would still have these, of course, regular APIs from Eclipse that you would need to use. And maybe since GraalVM is able to execute LLVM bitcode, I'm coming back to Doug and the C development tools and his efforts to re-implement the C++ parser in Java. So maybe with this technology, he would be able to reuse the Clang implementation for doing that. Not sure, but I guess the language server protocol is, at least from my point of view, the better alternative to implement different languages for Eclipse. So whenever you come across the GraalVM discussion on social media or wherever, you will see people talking about compiling native images. And that's what most people associate with GraalVM, which is not really true. GraalVM is not just about ahead-of-time compilation. It's there was the idea, okay, we have this great compiler that can compile highly efficient machine code out of bytecode and whatever. And then there was kind of the idea, oh, maybe we can use that as kind of a tiny little side project to do ahead-of-time compilation and produce native executables for Java programs. So how far can we get with that? It's kind of an addition or an additional tool for GraalVM that uses the GraalVM compiler to produce native executables out of Java code, JVM code. So why? Why should I do this? Why the hell should I do this? Because running the compiler in the OpenJDK with all these memory management or whatever, it's kind of, why should I do that ahead of time? It's producing the same machine code in the end, running at the same speed. So why should I do that? Of course, it's faster startup. If you're executing a JVM, you're kicking off a JVM, executing your thing, the compiler will kick in, compile your bytecode into machine code, and that happens every time you start up the JVM, which is great if you have a long-running application. If you have these server-side app server things or Spring applications that run on the server side, running for a long time, and maybe the C2 compiler kicks in after some time, collecting some profiling data under the hood to produce even better machine code over time. That's perfect, right? That's super awesome. But if you are in these kind of serverless environment where you have functions or small little snippets of Java code or smaller things, and you basically would like to kick off the process whenever you need it and shut it down right afterwards without keeping it alive all the time, startup time is really important and really interesting. And if you run the Java apps in the cloud space, having lower memory footprint could also be interesting. And if you're compiling your Java program into a native image using Graal, you usually use a lot less memory. No memory wasted for doing compilation stuff, keeping bytecodes around, and things like that. How does it work? That's at least the question that keeps me thinking. How does this all work? So what GraalVM does, if you compile stuff into a native image, is it takes your Java code, it takes the JDK libraries that you use, and it takes something that they call a SubstrateVM. It's something like a tiny little Java VM implemented in Java. Because in the end, you would like to end up with something that's kind of native executable, so it's not a Java VM anymore, real. They take all that code, which is mostly all written in Java, they do some static analysis on that. Because it's kind of a closed world assumption, right? They analyze everything, produce something like an intermediate model of that, and then they do the ahead of time compilation. So they compile all the Java code into native machine code. They are executing, if you want that, it's an option to be even better at startup. It executes static initializers of classes and does static stuff for you. So actually, a little bit, tiny little pieces of your program that you compile actually run while you're building the image, the native image. So it runs a little bit of your program, just the static stuff, and it snapshots the memory, the objects that get created. So it's kind of a snapshotting technology, and puts everything together so that in the end you end up with something like an initial heap, all the machine code packed into a binary, and you kick off that binary. And you can do that. This SubstrateVM is, of course, not a full implementation of the JVM, because you could imagine that Java is all about dynamic class loading. So dynamic class loading, that sounds strange in a native executable world, because you would like to put everything together into one big native executable. So you have this closed world assumption. There is no class loading allowed anymore. In the native image, you cannot do any class loading anymore. No class loading. Everything has to be known up front as a closed world assumption. Then everything gets analyzed by the native image builder, and that puts out the final executable, optimizing everything away. So everything that you don't use, everything that's not executed, anymore will not end up in the native image. If you have a class with 50 methods and only 2 of them are used, the remaining methods will not end up being compiled into the native image. They will be all ripped out. And stuff will be inlined and so on. Therefore, invoke dynamic and method handles are also not allowed, not available, not around anymore, as you might imagine. And other things are kind of limited and partly supported. You can generate proxies, for example, that you would usually generate at runtime, kind of dynamic proxy using JDK. You can do that at build time. So the proxy is generated at build time for you. But you need to tell the image builder which proxies you would like to generate. So you need to tell and educate the native image builder, hey, build proxies for these types. The same goes for reflection. Reflection is allowed, you can do that, but you need to tell the image builder up front what classes do we need reflection data about at runtime. So there's an implementation of the reflection API in the SubstrateVM that just more or less, if you go and say, hey, give me all the methods of this class, it looks stuff up in a table and see, oh, give me all the methods, what's in there. And this table, this data is generated at image build time. Therefore, you need to tell the image builder, please build up the reflection data as kind of static reflection data for these types, for these methods and so on. It's a pretty sophisticated thing you can tweak to not put too much data in there and so on. And the same applies to resources. If you would like to load resources like, oh, your properties file and things like that, you need to tell the image builder up front to do that. So let's quickly do that. Not everything, of course, but a little bit. So there's a simple command called native image. And you can configure that, but in this case, I cannot really configure anything because my example is so small and so stupid. I don't need to configure anything. I can just run the image builder. And the image builder does building the image in different steps, like collecting all the classes and doing all these intermediate model analysis and so on. In the end, it spits out a native executable from my Java application. That's hello world, a native executable on my machine, executing my Java stuff. And if we take a look at how fast it is, that's the Java version. That's the native image, roundabout. Just comparing startup times, right? So interesting exercise. Let's go back to the slides. Of course, the immediate question comes along and say, oh, is it possible to execute or to compile the whole Eclipse IDE into a native image? Wouldn't that be awesome? Compile everything into a whole big, huge native image and execute that. It would start up immediately. That would be awesome, but probably difficult because it's all based on OSGI, and OSGI is all based on dynamic class loading. And maybe you're used to install additional plugins, which would not be possible in a native image anymore and things like that. So I don't think that really applies. Native image building doesn't really apply to the whole Eclipse IDE. Interestingly, there is a new spec coming along for OSGI called OSGI Connect that allows you to tell OSGI how to find bundles and how to load bundles and things like that. So you can implement your own way of dealing with that. And I chatted with Tom, who works on the Equinox implementation, and he already kind of worked on something like that, implements the OSGI Connect specification based on the SubstrateVM, so that you could tell the native image builder, here are my 20 OSGI bundles, and please compile a native image out of them, and then you get a native image containing everything out of that. It's still early stages, right? Early days, doesn't really work out of the box on for every case, but it's interesting work, early steps, interesting stuff. So if you would like to know more about that, there's a reference to the project from Tom. Quite cool stuff. But up to now, I always talked about, yeah, running Eclipse, you can do that, but it doesn't really benefit. Okay, yeah. Compile native image, yeah, you can do that. Maybe not, and maybe it's not really feasible for the Eclipse IDE. So where should the Eclipse IDE benefit from GraalVM in the end at all? And I think the language server architecture could be a pretty nice fit for that. So we are implementing the Spring Boot language server, and we're putting that into the Eclipse IDE, and it starts up as an external process. So every time you open the Java file or something Spring related, it starts up the external process. So something like quick startup sounds nice, sounds great. Low footprint for these external language server processes. They're all running on your machine side by side with the IDE. That sounds pretty tasty. And maybe the peak performance is also not super extremely important for a language server. Peak performance like the server-side processes that run for a very, very long time, and the C2 compiler optimizes stuff along the way. So that's why I took that and thought, hey, let's convert our Spring Boot language server into a GraalVM native image. Let's try to do that. And indeed, I was able to get it mostly to work with all the limitations. And it's super fast to start up, and it's pretty good performance. So if you compare the startup performance that we have for the Spring Boot language server, running the Eclipse IDE on JDK 11 and starting up the external process, it takes about, let's say around about 2 seconds, a little bit less than 2 seconds to kick the whole process off and up to a level where we can really start doing something with the language server. So it's not pure JVM startup, it's really JVM startup, starting up the Spring Boot application. The Spring Boot language server is, of course, a Spring Boot application. We eat our own dog food, a little bit like that. And initializing the Spring Boot application, that takes about a little bit less than 2 seconds. It's not too much, but it is a little bit. If you compare that to the native image, it's more or less instant, right? You start it up, bang, it's there. So that's a huge benefit. That's cool. And as a second example, I tried to compare the performance. So we are doing a lot of AST parsing and parsing Java code inside of our Spring Boot language server, parsing everything and looking at everything and resolving types, reusing JDT for that, the JDT core library. So I compiled that into the native image. That works. That's great. It works for JDK or for Java 8 projects only because of the module file system loading mechanism. There's dynamic class loading being used inside of JDT to pick up the right Java file system implementation for that, for this module system, which totally makes sense, but it's a little bit complicated in the native image. So which version of that file system should I compile into the native image? I don't know, and maybe I need to change the implementation of JDT for that. Difficult. But I was surprised to see that if I'm running the Spring Boot language server on the C1 compiler, JDK 11, it took for my simple test case about 4 seconds or so to parse everything, which is pretty good. So pretty fast. Great parser, by the way. If you want to parse Java code, it's an excellent thing to use. And the GraalVM native image was actually pretty close to that, and even a little bit faster than the C1 compiler in the JDK, which I was surprised about. I thought it might be takes a little bit more, but as you can see for these, I think for these language server things, the Graal compiler and the native image stuff is a pretty good fit, I think. Okay, so that's kind of a brief overview about GraalVM and what I think it's useful for. So running Eclipse, you can do that, but maybe it doesn't make a lot of sense. But language servers seem to be, I think, a pretty good fit. And if you're willing to run 5 minutes into the break, I'm happy to answer questions, of course. So I forgot to tell you, you can ask questions anytime, which is always good to say in the end. So sorry for that. I forgot that. If you know me, you know you can ask questions anytime. Any questions?